The main goal of physics is to formulate scientific models. Models allow us to understand and predict the changes we observe in our surroundings and in the universe as a whole. Now, the world is a big, complicated place, too complex to take in all at once. Moment by moment, it's very natural to pay attention to the things that matter and to ignore those that don't. You do it all the time without thinking. Pay attention in class and ignore the text from your friend, or the other way around. When a physicist forms a model, that's what's happening in a more rigorous way. First, an imaginary boundary is defined around some part of the world. What's inside the boundary is called a system. Everything on the outside of the system is ignored unless it affects the system. Even inside the system, there are usually many details that can be ignored as well. In forming models, the scientist is a little like a referee in basketball. The basketball system consists of the ball, the court, the baskets, the backboards, and of course the players. Everything outside the system, like what kind of soda the dude in row 3 is drinking, doesn't matter, unless it somehow affects the action on the court. Some things inside the system, such as the team logo painted on the floor, don't matter either. To the referee, blocking out distracting, irrelevant details is as important as noticing what the players in the game are doing. Getting back to science, let's consider one of the most important models scientists have devised, the modern model of the atom. In this model, the atom is the system. The atom consists of protons and neutrons bound close to one another in a central nucleus, surrounded by electrons, wisps of matter so tiny that pinning their location down is impossible. The best we can do is make a drawing showing where the electrons are most likely to be found. Just as boisterous fans can affect the outcome of a basketball game, our atomic system can be affected from the outside. It can be chemically attached to other atoms. Its subatomic parts can be struck by free particles zipping through space. Changes can also happen within a system without influence from the outside. Electrons that have been pushed into higher energy levels will quickly return to ground state, giving off small packets of light called photons. In another example, the nucleus of an atom can spontaneously decay on its own. How do we know that the modern model of the atom is accurate? The same way we know whether all ideas in physics are good, by using the model to make predictions and then experimenting to see whether these predictions are correct. The framework provided by our modern model of the atom, atomic theory, allows us to make a wide variety of accurate predictions in physics, chemistry, biology, and beyond. When we formulate a model, we might ignore something that ends up affecting the system. Or perhaps we got some of the details inside the system wrong. Experimentation allows us to test our model. The best models are kept, the others are discarded. Devise an important model that stands the test of time, and you might win a Nobel Prize.